In this video, I will discuss two-dimensional motion, specifically projectile motion. Up to this point, we talked about one-dimensional motion, which is a motion that takes place right on the x-axis. Although rare in everyday life, but we found few practical examples. Projectile motion, on the other hand, is familiar to us throughout many daily activities. Almost every sport there is that involves a ball, whether you're kicking a soccer ball, shooting hoops with your friends on Saturday, kicking a field goal in football, hitting a homer in baseball, teeing off on Sunday morning, or simply tossing an object across the room. The motion of the object can mathematically be described by projectile motion. Before we sink our teeth into an example, I would like to cover some of the properties of the path of a projectile motion. If you look at the graph, the path looks like a parabola, and there is a reason for that. That means that the motion is described by a quadratic equation. As in many scientific experiments, there is a number of assumptions. The first assumption is air resistance equals zero, which means that the acceleration in the x direction is zero, and keep that in mind. Therefore, the x, which is the displacement in the x direction, equals x initial plus the velocity in the x direction times time plus 1/2 acceleration times time squared. This term here becomes a zero since acceleration is zero. So the x initial plus the initial velocity in the x direction times time. This simplifies projectile motion quite a bit. The truth of the matter is, projectile motion in real life is a very complex process, and assume that right here you have a gust of wind that pushes the ball into the screen or outside the screen. That would involve a z direction, and that makes it a three-dimensional motion, and that would complicate things quite a bit. Another property of this graph, that it's symmetric, which means this half of it is exactly the same as this half. The time it takes the ball to rise equals the time it takes the ball to fall. The total time is from when the ball leaves the ground until the ball gets back. Half of it is the ball rising and the other half is the ball falling. And if you think about it, to switch from positive velocity going up to negative velocity going down, it has to be a zero somewhere in here. So the maximum height is always at half the total time. That's also important to know. Anytime we study motion, there is always four concerns. The first one, displacement. The second will be velocity. The third will be acceleration. And the last will be time. Let's start with displacement. Displacement, here, as the ball leaves in this direction, it actually moves somewhat in the x direction and some in the y direction. So at every step of the way, there is two components to the displacement vector. So the displacement vector, if we call it r, will always equal the vector in the x direction and the vector in the y direction. The magnitude of the x direction is x equals x initial plus initial velocity in the x direction times time plus 1/2 acceleration times time squared. Well, we already agreed that acceleration in the x direction is zero. Displacement in the x direction is x equals x0 plus initial velocity in the x direction times time. Now, if the starting point here is the origin, which means x initial equals zero, this term also cancels out, and x becomes initial velocity in the x direction times time. And that kind of simplifies the matter quite a bit. Displacement in the y direction, y equals y initial plus initial velocity in the y direction times time plus 1/2 acceleration in the y direction times time squared. If the starting point is right here at the origin, y initial is zero. So y would equal initial velocity in the y direction times time and acceleration in the y direction. What we have here is gravity, g, which is 9.81 meter per second squared. And since it's acting downwards, it has a negative value. So it's minus 1/2 g times time squared. So far we have covered displacement. Next is velocity. Velocity is also a vector that actually, if you look up here, it changes direction. It has an x component, velocity of x, and it has a y component, velocity of y, and that's velocity itself. Going up, velocity in the x direction is constant. How do we know it's constant? Because we assume that acceleration is 0, which means it doesn't gain or lose any speed. So initial velocity in the x direction stays the same. What changes is velocity in the y direction, since it has an acceleration of negative g. If you look up here, velocity here is gaining distance, and as it gets to here, it becomes a 0, and then it loses distance, it retrieves. If you look at the shadow of the ball, it goes up, up, up until it reaches a certain point, then it goes down. So velocity changes. Velocity in the y direction, velocity of y equals the initial velocity in the y direction minus the acceleration times time. And this is the same as the one-dimensional motion equation. The one difference is initial velocity is usually given in two-dimensional terms. Next we have to cover acceleration, and I think we kind of went over acceleration as we talked about velocity. Acceleration in the x direction is 0. Acceleration in the y direction is negative g. So we have those. The last factor we have to talk about is time. And time is usually figured from one of these equations. The longest field goal in the history of the NFL was 63 yards, which is 57 meters. A very impressive record, I understand. I don't really know much about sports. But assuming no wind, when you assume no wind, that means there is no wind to knock the ball off its two-dimensional path, because that wind could actually push it into the screen or outside the screen. This means two-dimensional. And no air resistance. No air resistance means that initial velocity in the x direction remains constant, which implies 0 acceleration in the x direction. So x equals x initial plus initial velocity in the x direction times time plus 1/2 acceleration times. Since the ball is launched at the origin, that's 0 on the x and 0 on the y. This term becomes a 0, and this term becomes a 0. So x would equal v initial in the x direction times time. V initial in the x would equal v initial vector times cosine the angle in between, which is 45 degrees. Notice that sine 45 equals cosine 45. As the ball passes here, the elapsed time is t, and x equals 57.3 meters, y equals 3 meters. We're going to assume that the ball barely clears the post. So let's get started. X equals v initial cosine 45 times t, and we know x is the range is 57.3 meters equal the initial cosine 45 times time. And we know that cosine 45 equals sine 45, so in essence this also equals initial velocity sine 45 degrees times time. Y equals initial distance in y plus initial velocity in the y direction times time minus 1/2 gravity accelerations times square. This term is 0. Y equals 3. Y initial is 0 plus the initial velocity in the y direction is initial velocity times sine theta, which is 45 degrees, times time minus 1/2. Acceleration of gravity is 9.81 times square. So 3 equals This term here is exactly this term, which equals 57.3 meters. So 57.3 meters minus 9.81 divided by 2 is 4.91 times square. So 4.91 times square would equal 57.3 minus 3, and that equals 54.3 times square equals 54.3 meters divided by 4.91. Let's do the units here. This is distance, so this is meters, and this here is acceleration, which is meters per second squared. The meters cancel with the meters, and since the seconds are inverted, this answer here would be seconds squared. And that matches because we have time squared. Let's bring the calculator and figure out how much that is. 54.3 divided by 4.91, and that equals 11.06. So this here is 11.06. And for your time, this would be the square root of 11.06. And that equals 11.06 square root. And that's 3.33 seconds. 3.33 seconds. We still need the initial velocity. We know when the ball passes here, the time here is 3.33. That's the time elapsed since the ball was launched. And to figure the initial velocity, we could use this one here. X, which is 57.3 meters, equals initial velocity, cosine 45 times time. 57.3 divided by cosine 45 times time, which we know time was 3.33 seconds, equals initial velocity. 57.3 divided by cosine 45 times 3.33. Initial velocity 24.35, and that's meters per second. So the initial velocity here at 45 degrees is 24.35 meters per second. Watch my next video for more examples on projectile motion.